All right. So we're going to talk about 12.4 part 2. We're going to talk about tangential and normal components of acceleration. So last time we talked about finding how we find a unit tangent vector and a unit normal vector if we have some vector value function r of t, and we said we could interpret r of t as a position vector and our other vectors, r prime, etc., as velocity, acceleration, that kind of thing. So we had this with this vector valued function. So we came up with a way of finding a unit tangent vector. So let me draw a curve here. So let's say this is r of t. This is the curve that describes r of t. So we came up with we said our velocity was tangent to the curve, and we could use that to find a unit vector tangent to the curve. And then we came up with the process of finding a normal vector from the tangent vector, and we said the normal vector always pointed towards the concave side of the curve. So just graphically, this is what we're looking at. And these both, I guess we should, just to make it explicit, these vary with time. So as we move around, these are going to change. And these two are orthogonal to each other. The way we constructed them, those are going to be orthogonal. So what we want to do today is break down acceleration, or the second derivative of our position vector, into a component that is tangent to the curve and a component that is normal to the curve. So before we do that, let's think physically about what we're talking about here. So a tangential component of acceleration, what would that be doing to whatever our object, our particle, whatever it is that's moving along this curve? What would tangential acceleration be? So acceleration along in the direction of our unit tangent vector. Speed it up or slow it down. So our tangential component of acceleration is we're talking about speeding up and slowing down. What would the normal component, if we had a component of the acceleration normal to the curve, what is that going to do to our object? You change direction, rotate, make it turn. So we're talking about a type of acceleration that speeds up or slows down our object, and a component of acceleration that's going to tend to make our object turn. So we want to break our acceleration into those two components. All right, and we're going to use our unit tangent vector and our unit normal vector that we talked about last time to come up with this way of describing acceleration. So we defined t. Our unit tangent vector was defined as r prime over the magnitude of r prime. So let's call the velocity vector we'll call it v. So we'll say this is the velocity vector, and we're going to say that just v without the vector is the magnitude of our velocity vector, and we're going to call that the speed. So the magnitude of our velocity vector is the speed, and we said that our principal unit normal vector was, if we use this this notation, we said that, no, I've got my brackets here, that the principal unit normal vector was t prime over the length of t prime. And we saw with a pretty easy example that we did with relatively easy position vector that this principal unit normal vector can be algebraically kind of a mess to find. We're gonna talk about a shortcut, another shortcut. We talked about a shortcut in the plane on Friday. We're going to talk about another easier way sometimes to find this principal unit normal vector. Now I'm going to, usually what we want to do is express these in terms of our position vector or derivatives of our position vector. So what I'm going to say is, using this notation, I'm going to say that t, our unit tangent vector, is the velocity vector over the magnitude of the velocity vector. And I'm dropping the t's here just to make it easier to write. So we can say that our velocity vector is the speed, the magnitude of the velocity, times our unit tangent vector. And what we're going to do is differentiate this expression to come up with an expression for our acceleration. We're going to differentiate. So I'm going to differentiate this quantity. So I'm going to say that the derivative with respect to time of our velocity, and our velocity does vary in time, equals the acceleration, and we're going to differentiate this quantity. So this is going to be, we're going to use the product rule here. So we get the rate of change of the magnitude of v, of the speed, with respect to time, times our unit tangent vector, plus the magnitude of our velocity, the speed, times the rate of change of our unit tangent vector with respect to t. And then we're going to rearrange this and work with this a little bit. So looking at this quantity, what's another way we can write dt, the rate of change of our unit tangent vector with respect to time, that we've used previously? How about t prime? dt equals t prime. So I'm going to substitute this in. So our acceleration is the rate of change of the speed with respect to time times our unit tangent vector plus the magnitude of the velocity times t prime. And t prime is related to our principal unit normal vector. So let's rewrite. Now I'm going to multiply here by a convenient form of 1, so I can write this expression in terms of our principal unit normal vector. So I'm going to multiply this part by the magnitude of t prime over the magnitude of t prime. So we want to write this in terms of our principal unit normal vector. So I'm going to get my acceleration vector is the rate of change of the magnitude of v with respect to time times our unit tangent vector plus the magnitude of v times t prime, and then I'm going to multiply by the quantity magnitude of t prime over the magnitude of t prime. Well, t prime over the magnitude of t prime is our principal unit normal vector. So I can write that, finally, that our acceleration is the rate of change of the speed times our unit tangent vector plus the magnitude of our velocity times the magnitude of t prime. Remove my plus sign here. All my magnitudes are getting mixed up together here. Times the magnitude of t prime times our principal unit normal vector. I'll write this a little more neatly. There we go. Yes?
So why do you only multiply half the
Well, we want to, here, for this first term, so the magnitude of t prime over the magnitude of t prime is just 1. So it doesn't change anything. So this first term, we already have some expression times the unit tangent vector. So here we are trying to rearrange this to get some expression times the unit normal vector. So we wanted to change this so we had the unit normal vector involved there. So that's why we chose to multiply by magnitude of t prime over the magnitude of t prime. And we can say from this that our acceleration is, we'll call this first a sub t times the unit tangent vector plus a sub n times our unit normal vector. So this is our tangential component of acceleration, and a sub t is the rate of change of the speed with respect to time, and a sub n, the normal component of acceleration, is the magnitude of the speed times the magnitude of t prime. So what we've accomplished here is written the acceleration vector as a component tangential to the curve and a component normal to the curve. So we've broken our acceleration vector down into those two components. And we've accomplished two things by doing this. We accomplished two things. We found expressions for the tangential and normal components of acceleration. And I'm going to switch pages here. So we found our components, our tangential and normal components of acceleration. That was our goal, to break our acceleration into components that are tangential to the motion and a component that's normal to the motion. So we got two things. We found our tangential component and normal component of acceleration. So that was part of our goal. Two, the second thing we've accomplished here is, since our acceleration can be written as a linear combination of our unit tangent and our unit normal vector, Our acceleration is always in the plane defined by those two vectors. So there are no components of acceleration that are going to take us out of that plane. So our acceleration is always contained in the plane that's defined by t and n. And t and n are, because of the way we define t and n, they're two vectors, so they're always going to define a plane. So our acceleration is always going to be in that plane defined by t and n. Well, this gives us another way to work with this acceleration because it's always in the plane. What we can do is, let me draw a picture here. So here's our curve again. Draw that in red. And this is the curve given by our vector valued function. And let's say our acceleration at some particular point is, let's say the acceleration is here. So that's my acceleration vector. Well, I have a tangential component of acceleration. I'll do that, do those in black. So we have a tangential component of acceleration, like so, and a normal component of acceleration, like so. So there's our unit tangent vector and our unit normal vector. If I project this onto the vector here, project our acceleration onto this vector and onto that vector, because the magnitude of t and the magnitude of n are 1, I can say this length is a dot t, because the magnitude of the unit tangent vector is 1, and I can say this length, the normal component of acceleration, is a dot n. Now because the magnitude of t and the magnitude of n are both 1, they're both unit vectors, this projection is given by the dot product. So because these are both in the plane defined by n and t, we can say that a sub t is also equal to a dot t, and a sub n is the acceleration dot n. And again, we can say this because the magnitude of t equals the magnitude of n, and they're both unit vectors. So our tangential component of acceleration is also given by the dot product of the acceleration with the unit tangent vector, and the normal component of acceleration is given by the dot product with the normal vector. This gives us another way to work with these. Because what we normally want to do is we want to be able to express the tangential and normal components of acceleration in terms of r prime, and r double prime. We don't want to have these unit tangent vectors and the unit normal vectors in there. So we want to express these components of acceleration in terms of our position vector, our velocity vector, and our acceleration vector. We don't want to have these t's and n's in here. And because because of this fact, because the acceleration is in the plane defined by t and n, we can write this, a linear combination. We can use these expressions. And then what we're going to do is, and I'm not going to go through the derivations, but we can go through, I'm not going to go through them in class, but we want to look at three quantities. We look at the velocity, dot the acceleration. We look at the velocity crossed with the acceleration, and we look at the acceleration dot acceleration. We look at these three quantities. We go through the process of forming these dot products. We use this expression that we came up with for our acceleration, and we form those dot products, and we manipulate those. I do all of these derivations on a separate video that I strongly suggest that you watch. It takes maybe 10 minutes or so. On the video, Calc 3, 2013. It's tangential and normal components of acceleration derivations. So I go through the process. It's not a long process. I just don't want to do it in class. We go through the process of forming these dot products and these cross products and simplifying the expressions that we get. So I go through that in this video. It's nice to watch those because you see how we use what we know about the dot product, how we use what we know about the cross product, and the unit normal and unit tangent vectors to come up with nice, easy to work with expressions for our tangential and normal components of acceleration. So we don't have to deal with these unit normal and unit tangent vectors because we saw that those can be difficult to calculate sometimes. So we go through these, forming these products, simplify them. The results that we get. The formulas that come out of those derivations. First off, we've already done this part. We said that our acceleration can be written a sub t times our unit tangent vector plus a sub n times our unit normal vector. If I rearrange this, I get an expression that is much easier to calculate for our unit normal vector than t prime over the magnitude of t prime. So I can rearrange this and I get that our principal unit normal vector is the acceleration minus the tangential component of acceleration times t, all divided by a sub n. This quantity is often much easier to calculate than t prime over the magnitude of t prime. And we'll come up with ways to calculate a sub t and a sub n. I'll write those down in just a second. Those come out of those vector derivations. A sub t. The first quantity we came up with for a sub t, our tangential component of acceleration, was the rate of change of the speed. We also said that that was a dot t. We find that this is also equal to v dot a over the magnitude of v. So this gives us a way to calculate the tangential component of acceleration without dealing with this unit tangent vector. And that comes out of rearranging, working with this quantity and rearranging it. We find that a sub n, our first expression for a sub n was the magnitude of the speed times the magnitude of t prime. That's what we got from taking the derivative. We also said that that was a dot n. And when we find v cross a and simplify that, we find that that is the magnitude of v cross a divided by the magnitude of v. So this gives us a easier way of finding a sub n. We don't have to deal with this magnitude of t prime. V cross a over the length of v. And finally, by forming a dot a, we find that a sub n is also equal to the square root of the magnitude of the acceleration squared minus a sub t squared. And often this last quantity is the easier way to find a sub n, the normal component of acceleration, versus forming this cross product. So these three quantities, this one, and this one, are what we come up with on that other video, by working with the dot products, those dot products and those cross products. So these three are the ways, the most common way that you're going to find your tangential component of acceleration, your normal component of acceleration. And this gives you a convenient way of finding the principal unit normal vector without having to find t prime over the magnitude of t prime, which we saw on Friday can sometimes get to be a lot of work. All right, so just to recap what we've just talked about. We've looked at a vector valued function as describing the position of some object. We wanted to break down the acceleration into a component of acceleration tangential to the curve and a component of acceleration normal to the curve. We first did that by taking derivatives. Just form the derivative and rearrange that a little bit. That's where we got these expressions. So our tangential component of acceleration is the rate of change of the speed, which we call the scalar acceleration. The normal component of acceleration is this quantity, magnitude of v times the magnitude of t prime. We also said that because this expression is a linear combination of t and n, that our acceleration is always in the plane defined by t and n. And that let us form these dot products to find our tangential and normal components of acceleration. So if we already know our unit tangent vector, unit normal vector, these are convenient for finding a sub t and a sub n. And then we can go through the process of working with some other quantities to come up with these other expressions for the tangential component of acceleration and the normal component of acceleration. And that was the entire goal of what we were talking about. Questions about what we were doing? Now what we're going to do with the tangential component of acceleration, normal component of acceleration, is for this chapter, we're going to use these ideas to the last couple of lessons that we'll talk about have to do with curvature, and we want to quantify the curvature of some curve in space. And these tangential and normal components of acceleration, these expressions, are going to give us a tool to quantify curvature. Curvature is one of the fundamental properties of a curve or of a surface in space. Yes.
So you ever have to work backwards from a to t base and then find the acceleration?
Possibly. But any kind of problem like that is you would have all different pieces of information you would need to put that all together. All right, so what I want to do is I want to go through one example of calculating, finding a sub t and a sub n. I also go through the example that we'll do in class, and there's an additional example, and you can find that on a separate video if we run out of time. So that's posted on Calc 3, 12.4 examples. So I want to start through one example. We might not get all the way through. I think we should be able to get through the one. And then there's a second example on that video where we go through the process of finding all of these quantities. All right, so let's start through an example. So we'll start with a nice, not a very complicated curve in the plane, t squared I plus 2t j. And for this we want to find our unit tangent vector, our principal unit normal vector, our tangential component of acceleration, and our normal component of acceleration. And we saw in what we just talked about, all these are kind of all tied together. And we're going to say at t equals 1. So we need to find some derivative. So r prime, we need r prime. So r prime is going to be 2ti plus 2j. And the magnitude of r prime is the square root of 4t squared plus 4. And we want these quantities at t equals 1, so r prime of 1, to find t, our unit tangent vector at t equals 1, r prime of 1 is 2i plus 2j, and the magnitude of r prime at 1 is going to be square root of 8, or 2 square root 2. So finding our unit tangent vector, not too tough there. So t at 1 is 1 over 2 square root 2 times 2i plus 2j. To find a sub t, I'm going to use this, v dot a over the length of v. So we need our acceleration, our double prime. Our double prime is 2i. And that's going to be a constant, so we have a constant acceleration here. So I'm going to say that a sub t, our tangential component of acceleration, is, and we want this at 1. Our velocity at 1, dot product with the acceleration at 1 over the magnitude of v at 1. So that's how I'm calculating this tangential component of acceleration. Well, we already found r prime is our velocity, r prime is v, and we found the magnitude of our velocity. So all we need to do is find the dot product of r prime at 1 with the acceleration at 1 for our numerator here. So this is going to be 2i plus 2j. We're going to form the dot product with 2j, and we're going to divide that by the magnitude of v, which is 2 square root 2. 2i, yes. So we just end up with square root 2. And that is our a sub t at 1. Our tangential component of acceleration at time equals 1 is square root 2. And if the problem had asked us to find an expression for a sub t in general, we would just use our vector notation to come up with this, and we would get a sub t as a function of t. They were nice and just asked us at t equals 1. All right, and then we're going to find our normal component of acceleration at 1 is going to be the magnitude of our velocity vector at 1 cross the acceleration vector at 1 over the magnitude of v at 1. So I'm using this expression for our normal component of acceleration. And we've calculated, we found all of these quantities already. So this is, we need to find our velocity cross our acceleration. So our velocity at 1 cross our acceleration at 1, then we'll find our magnitude. A is our determinant, I, J, K. We have 2, 2, 0, and 2, 0, 0. We find our cross product. This turns out to be negative 4 k hat. So the magnitude of this cross product is just going to be 4. So now we have everything we need for a sub n. So a sub n, our normal component of acceleration at time equals 1, is going to be 4 over 2 square root 2, which also comes out to be the square root of 2. So we found our tangent vector, unit tangent vector, our normal component of acceleration, our tangential component of acceleration, and now we're going to use this expression to find our principal unit normal vector. So we don't have to find t prime over the length of t prime. So in our principal unit normal vector at time equals 1 is going to be our acceleration at 1 minus our tangential component of acceleration at 1 times our unit tangent vector at 1, all divided by our normal component of acceleration at 1. And we have all of those quantities. So that's going to be 2I minus square root of 2 times, and I've rationalized my denominators here, for our unit tangent vector. And this is all divided by the square root of 2. And when I simplify that all out, I get the square root of 2 over 2I minus square root of 2 over 2j. And that's my principal unit normal vector at time equals 1. And this is much easier calculation than finding t prime over the magnitude of t prime and evaluating that at t equals 1. So we found our tangential component of acceleration our normal component of acceleration, our unit tangent vector, and our principal unit normal vector for that particular curve at time equals 1. So you can see, even for a relatively simple vector value function, there's a lot of calculation involved there. Not necessarily difficult, but a lot of calculation. What's another way, without using the formula here because we're in the plane? What's another way I could have found our principal unit normal vector at time equals 1 from this formula? Because we're in the plane. Remember what we talked about Friday? Our shortcut? Switch the x and y's, change the sign on 1. So here, this is the same as square root of 2 over 2i plus square root of 2 over 2j. And our principal unit normal vector is square root of 2 over 2i minus square root of 2 over 2j. So I switched the sign on the y component. The only difficult part with that shortcut is we need to know which was pointing towards the concave side of the curve. So we're in the plane. When we're in the plane, we can switch the x and y's, change the sign on 1, and we just have to figure out to decide which way to change the sign, we need to know which vector points towards the concave side of the curve. All right, questions on what we did there? All right, there's another example on that video that I mentioned, a three-dimensional vector value function with a k component. So there's a little more going on there, not a lot more, but you can watch that second example on the YouTube channel. Questions? Okay. All right, there you go.